Good morning. Today we're going to be taking a look at Unit 9, Day 1, Taylor and Maclaurin series. So what our goal for today is actually we are trying to find a polynomial that is able to model something that's not a polynomial, so like a sine and e to the x or ln. So the advantage of being able to do that is we know that it's usually a lot easier to work with polynomials in terms of it's easier to take a derivative of a polynomial, etc. So we want to be able to approximate sine or other functions with a polynomial. So we'll kind of start today with on your calculator. I went ahead and on the calculator, when I put in my y equals, I went ahead and graphed sine, and then I also put in this here, and you'll see where that kind of comes from in a few days, but I wanted to kind of graph that. So, and I did have my calculator put in radian mode, and then I choose zoom 4 from the list. So there you have your sine curve. Hopefully you recognize that. And then I have this polynomial that's coming in. And what I want you to notice is that it's kind of overlapping, the red curve is overlapping the blue curve from what appears to be about -2 to 2, give or take, okay? So it kind of looks like it's overlapping it for that period of time there. So I'm going to kind of move that to the side. So it seems like the two graphs overlap from, I'll just say from about x equals -2 to x equals 2, give or take, okay? So now I want to take a look at what happens. So I'm just going to go back to that y equals, and on my y2, I'm going to go all the way to the end there, and then I'm going to add on an additional term, okay? So for this one, it's a negative, so I'm actually going to subtract. So minus, and then I'm going to say x raised to the 7th, arrow out of there, divided by, and then I'm going to put on a 7 factorial. Okay, so that's under math, probability, choice 4. Close, close. And now I want you to take a look at what happens now. So I still have my original sine curve, okay, that blue curve. I know what a sine curve looks like. And now the polynomial is going to be coming in the red. And now what you'll notice is it starts overlapping. It looks like a totally different polynomial. It's coming from a different direction. But now that part where it's overlapping the blue curve seems to have extended. Instead of being from -2 to 2, now that overlap seems to be, I'm just going to say the overlapped area. So the overlapped section increases, okay? Increases to from about x equals -3 to x equals 3. So now I'm kind of overlapping for 6 units instead of just 4 units like I was up there. And so I wanted you to see that kind of visually because remember, our goal is to be able to approximate a sine curve using a polynomial. So if I wanted to know what, say, sine of 1 was, instead of having, I don't know what sine of 1 is off the top of my head, but I could probably plug in x equals 1 into a polynomial and be able to figure out what that is. So the idea is that if I get a polynomial that overlaps a curve that is more difficult or more challenging to work with, that if I find a good polynomial to kind of model that, then I'm going to be able to use that polynomial. So that's kind of what we're going to be tackling today, okay? So with that, we're going to kind of go into this polynomial function we've got there. Okay, so I've dropped in the formula for, this is a polynomial of the nth degree here of x. So what you're going to do, we have f of c, okay, where c is going to be where your center is. And then you'll notice it's plus the first derivative evaluated at c multiplied by, how far off from that center you are, okay? Then you'll notice the second derivative at c over 2 factorial, and you kind of see the pattern. You can keep it going. So it's here's the first, then the first derivative, second derivative, third derivative, okay? And then we're evaluating it at where you're centered, and then we're multiplying by that polynomial is increasing in degrees. So obviously a third degree polynomial, you would only have these first terms here where the highest exponent is a 3, okay? And then it goes plus, so the derivative, whatever degree you're taking there over that factorial to that power. So those kind of match, and you can kind of see the pattern in there, okay? And so a special type of polynomial where you're centered at 0 is actually called the Maclaurin polynomials, where c equals 0. So you can kind of use this same formula, but if c equals 0, then it's just kind of a special version of it there. So once you have that formula, we can start to write what these are. So I'll kind of go back to the other one there. Okay, so in this example, we are given f of 2 and the evaluation of a bunch of derivatives at 2, and they're asking us to write the Taylor polynomial of degree 3. So let's kind of pay attention here. So degree 3, that tells us that n equals 3, and this is centered at x equals 2. So that tells me that c equals 2. From there, it's just a matter of kind of popping it into that formula there. So we have a polynomial of degree 3, okay, and our variable is going to be x, so we would represent it like this. And so now we're just going to say it's going to be f of 2, kind of where you're centered, and now we're going to have to take the derivative at 2 multiplied by x minus 2. Now I go to the second derivative part, so it's going to be the second derivative. Technically, this is over 1 factorial if you're looking for that pattern. Then we're going to do the second derivative at 2 over 2 factorial. And then the variable term will be x minus 2. And again, this now has to increase the degree. So you go from degree 1 to 2. Obviously, this piece would be degree 0 there. And I still am not done yet. I need to go to a degree 3, so I'm going to do plus. Now I'll need the third derivative at 2 over 3 factorial. And we're going to multiply that. I got to kind of squeeze it in there. That to the third power up there. Okay, so I had to kind of squeeze it in. This is kind of my general setup. Now I can use the given information to fill in. So we're going to say that my final answer then would f of 2 is 3. So this piece would give me a 3 minus 4. Got that there because it's a negative 4, so it becomes a minus 4. And then I've got x minus 2. You leave that alone. And then plus, now I've got a 7 as the value for there, so you get 7 over, you could leave it as 2 factorial, or 2 factorial happens to be 2. But again, on a lot of these, you're going to want to just leave the factorials in your answer, okay, because you're not going to want to simplify those out. So then a minus 5, and then again, 3 factorial. You could write 6 or leave it as 3 factorial, depending on if it's a multiple choice or anything like that. And so we're just kind of plugging it in. So with that then, you would be done with this problem, okay? This would be a polynomial. If I kind of plugged this in, then all these things would be true, okay? So let's go ahead and take a look at the second example. Okay, so the second example, they didn't give us any of the evaluations here, so it's different. So it says, find the Taylor polynomial of degree n for e to the 3x centered at x equals 2. So this table to organize is something that I gave you. They will not give you a table, so you'll have to kind of create that. But I just wanted to do these first few with something to kind of organize it. So what did they give me? Well, it's centered at 2, okay, and they gave me the function. So I'm going to write that here. So that's e to the 3x. Now notice, I have to take, if you look at that formula again, you have to take all those derivatives, right? So if you kind of look back to this formula, notice that I need what f of c is. I need the derivative, the second derivative, the third derivative. So what I'm going to do is I'm just going to take a bunch of derivatives until I get to n equals 4. So we kind of start at n equals 0, and then I'm going to take the derivative. So the derivative of e to the 3x, remember you copy it, multiplied by the derivative of the junk up there. So we got a 3 there. Similarly, to take the derivative of this now, I would recopy it, multiplied by 3 again. So this is actually going to become a 9. Okay, the derivative of e to the junk is e to the junk times the derivative of the junk. Again, I would recopy this, but then multiply it by 3. So this is going to become a 27, e to the 3x. And then one more time, that's going to give me a big old 81, e to the 3x there. So I kind of took all those derivatives, and now this says I'm plugging in x equals 2. So if I plug in x equals 2 there, I get e to the 6th power, and then I'd get 3e to the 6th, and so on and so forth, 9e to the 6th. I wouldn't take the time to necessarily do this huge table every time, but since we're kind of just getting started with these, I would kind of help you organize it. Okay, so I took a bunch of derivatives, and then I was plugging in to those derivatives where I was centered. Okay, so I plugged in the c value to get where to evaluate the derivatives there, and now I'm writing a 4th degree polynomial. So we kind of say it p4 of x. Okay, this is a 4th degree polynomial that would model this. Okay, I'm trying to model this, and where I'm centered, that's going to be, the closer you are to the center, the more accurate the model. So this would be good to estimate e to the 3x at, x equals 3 or x equals 4, but it would not be so good, at x equals 27, okay? The further from the center you get, the less accurate the approximation. So if I was kind of turning this into there, I would say it's going to be, okay, e to the 6th, right? There's the first part. Now I have to do this one. Don't forget then, you got to tack on the next piece. So all I'm doing now is plugging into this general formula. I had e to the 6th. Now I need the derivative, and I'm multiplying by x minus the center. So I'm just going back to that same formula and plugging them in. We're kind of dropping them in there, really. And that'll be x minus 2. The power there is just a 1. Plus, now I do this one. So it's 9e to the 6th over 2 factorial. Again, you could leave it as 2 or 2 factorial. Multiplied by x minus 2. Now I'm squared. Okay. For time, I'm just going to go down to this next line so that everything kind of fits, but it's still plus. The next term would be 27e to the 6th over 3 factorial this time, and then it's going to be x minus 2 to the 3rd, plus, then the last one there, I've got 81e to the 6th over 4 factorial multiplied by x minus 2 to the 4th, okay? I always kind of check it and make sure I go 4, 3, 2, 1, 0, right? Kind of watch your patterns, check your answers in between there. So now you wrote a polynomial. So what this is saying is that this polynomial is going to model this f of x near x equals 2, right? So you could go maybe to 1, maybe to 3, right? It would be pretty accurate between those. And if you wanted to see, again, all you'd have to do is pull out your calculator and type those in. Okay, for example 4 here, have your calculator handy because we're actually going to kind of check our answer using the calculator. But we're going to kind of do that process the same way to start out. We're going to say, all right, we're working with f of x here is sin x, so I'm going to write sin x there. And here we're trying to figure out a 5th degree polynomial. And this here tells me that c equals 0. Okay, so that tells me that c equals 0. So I start by taking a bunch of derivatives. So the derivative of sine is cos. Derivative of cos is negative sine. Derivative of negative sine is negative cos. Right? And then we get back to sine again. And then we're going to go to cosine again. Okay? So I just took derivatives going down. Again, this kind of table won't be given to you on the AP exam or anything, but for these first couple, it's just kind of a way to organize my thoughts. Now what I'm going to do is I'm going to take x equals 0 and plug it into there. So I'm going to say sine of 0, which we know from our unit circle, sine of 0 is 0. Then we're going to say cosine of 0, which we know is 1. Negative sine of 0 is 0. Negative cosine 0 is going to give us a negative 1, right? Because cosine of 0 is 1 times negative 1 gives me negative 1. And then back to the top again, right? I'm going to get 0 and 1 again. So you kind of see this pattern there. So, okay. And that's going to kind of play a role when we kind of look at what our Taylor is later. But here we're writing a polynomial of degree 5. Okay, our variable is x. So that's our notation there. And so when I go to write it, I have 0 for the first part. And again, I'm going back to that original formula, right? So Now what I'm doing is I have to take f of 0 plus the derivative at 0 times this, right? I'm just going back to that same thing and plugging in. So I get 0 plus, now it's going to be 1 times x minus c, but in this case, c is 0. So if you don't want to put the 0 there, you don't have to. And then plus, I've got 0 divided by 2 factorial, okay? And again, x minus 0 squared. And I'm just following the pattern. Again, a bunch of these things are going to drop off when I simplify it, but for now, I'm just going to kind of put them in there so that I follow the pattern that I'm used to. Okay, and then the 4th degree, right, 0 over 4 factorial, x minus 0 to the 4th, and then I'm going to have plus 1 over 5 factorial, x minus 0 to the 5th, right? And so I can kind of clean that up. Okay, we don't need this 0. We know this is really just x, right, minus, and then I've got 1 over 3 factorial times x cubed, right, because this piece goes away. This cleans up to there. This is going to end up to be 0, so this whole piece goes away. So now I'm working on this piece here. That's just going to be x cubed. And then I've got plus, this piece goes to 0, right? 0 divided by anything is 0, so this whole term is gone. So I've got 1 over 5 factorial x to the 5th. Okay? So how would we use this? And we kind of started off with this f of x equals sign. So how are we going to use this now? On your calculator, since I've got that in there, I'm going to do this for just a moment here. So let me turn on my calculator. I'm going to go back to my y equals. I'm just going to clear the sign out of there. And keep in mind, that's exactly what I typed in down here. I've got that typed in, and I only have until the 5th term. So I just got to go in here, and I'm going to delete out those extra things that we had inserted in there. Delete, 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 clean that up. All right, almost. Delete and delete. Okay, so if I was just graphing this polynomial, so all I did was throw this into my y equals. Now say I wanted to figure out what the polynomial was evaluated at 1.4. So you could either plug 1.4 in there using your calculator, you know, just in your regular home screen or whatever. If you already have it in your y equals, one advantage of the calculator then, I'm just going to do second calc value, and then I'm just going to type in 1.4. So my calculator, I don't know if you can see that, but I've got, I'll round to 3 decimals, so I've got 0.987, okay? So my polynomial gives me this 0.987 at 1.4. Now notice 1.4 is relatively close to the center, which mine is centered at 0, okay? So now if I wanted to evaluate the function at 1.4, really that's saying plug 1.4 into sine. So I'll just go back to my home screen for that. Again, I could graph it and do second calc value, but it's probably easier here just to do sine 1.4. Again, I'm in radian mode. So I get 0.985. So 0.985. So you can see these two numbers are pretty close, meaning my polynomial is doing a very good job of approximating the sine graph when I'm relatively close to that center. Okay? So if I had, and this is a 5th degree, so again, this tells us that a 5th degree polynomial is a pretty good approximation at x equals 1.4. And so the error is just the difference between those two numbers. So I get 0.002, right? If you subtract those, I'm off by 2 thousandths. That's pretty good. And so then, if I did the same thing, but I wanted to do, evaluate it at 2.1, so I'm going to go back to my graph here and do second calc value. And now I'm going to try it at 2.1. Again, this is approximating using the polynomial. This time I got 0.897. And then if I wanted to figure out what sine of that was using my calculator, I could type that in. And I'm just doing this, normally these questions on the AP exam would not be calculator active, but I'm just trying to show you what you're actually doing. We're creating a polynomial that approximates a function that's, you know, not very nice, like a sine curve or something like that. So what you'll notice here is that I'm still pretty close, but I've definitely lost some of my accuracy here, right? The error this time is 0.034, right? If you subtract those, you get to there. And so as I move further away from the center, recall this one is centered at 0, as I move further away from the center, my approximation is not as good. And you can kind of recall that from when we graphed it, right? The overlap was really good, you know, when you're kind of near the center of it, but then you kind of get a little bit further off. So it's not exactly, but it kind of gives you a pretty good. And as you move further from the center, the error was larger, okay? So if you're just trying to kind of do that. So the error was larger when you were estimating using the 2.1, and the error increases as you move further away from the center. Okay, so that's kind of a crash course in Taylor polynomials. I encourage you to kind of go ahead with the homework, and then let me see if there's anything on page 4. Just be careful. I actually am going to go ahead and do example 6. Okay, I'll go ahead and do an example 6 from your notes, and then we'll kind of leave you off there. All right, so now with example 6, we've got some information here. It says we are approximating near x equals 4. It's a third degree, right? So n equals 3. My center is 4. And they gave me this. Now, I need you to look at this very, very carefully because something is missing. Notice you go from, you have the third power, the second power, but you're missing the quantity x minus 4 to the first power. That's really important, okay? So in other words, you don't have a linear term. There's no linear term there. So that's going to give us a valuable piece of information, okay? If you go back to page 1, right, if you're looking at this, guys, when you're doing it, if this term here is no longer there, what does that tell you about the derivative at that point? Well, the only way that this would go away was if this piece was 0. So what that tells me, since I'm missing that linear term, that tells me that the derivative, right, at 4 must be 0. And that's really gives us some other important information as well, because we know that if the first derivative is 0, that means that there must be a critical value at x equals 4. What's that?
Oh, hey, Ms. Law.
What's that?
I heard we have a test tomorrow.
Yeah?
Okay. Then I'm here to study.
Okay.
Yeah. Are you making a video?
Yeah.
Okay.
Can you study quietly? I'm on the last one that I'm going to do. I probably only need like 2 more minutes. Okay. What do we got? Oh no, did I freeze it? Oh no. What happened? Pause. Why isn't it pausing? Oh, Zen.
What did it do?
I don't know, you messed it up.
I didn't do anything.
Okay, sorry about that. I'm having some technical difficulties. It's Zen's fault. But, so we've got a degree 3 polynomial, and so we know it's going to be f of 4 plus the derivative of 4, right, times this x minus 4. So this is kind of my general formula here. But since I know that the derivative at 4 must be 0, right, then I take this, and that gives me a piece of info. So what does that mean? It means this 2 then tells me that f of 4 equals 2, okay? So if f of 4 is 2 and the first derivative is 0, then I know that this second derivative over 2 factorial must be that -5. You're kind of matching this piece here to this right here, okay? So if I know that the second derivative evaluated 4 divided by 2 factorial must be -5, you can cross-multiply there and solve for your second derivative. So 2 factorial is 2. 2 times -5, right, gives you that -10. So if I know that the second derivative at 4 is -10, okay, so I've kind of figured this piece out, I figured that out, I figured that out. Now I need to do the third derivative. So your third derivative evaluated at 4 divided by 3 factorial, according to this, must be 8. So then you're just going to cross multiply, and then you can solve for the third derivative there. The question then takes it one step further. Using your second derivative test, this is one that I think most of my students weren't a huge fan of. Then determine if it has a local maximum or neither. So the second derivative test says, right, take a look at the if you have a critical value, which we know we have a critical value because there was no linear term, okay, so we've established there's a critical value there, and then we can look at the positivity of the second derivative. So since there's a critical value at 4, and we know that the second derivative at 4 was negative, right, then it must be concave down. And if the function is concave down there, then we must have a local maximum. Okay, so you can kind of put all that together, and then we'll take a look at some more Taylor stuff next class.